chip tape-out projects. He published a few research papers in national and international journals. Currently, he is working as a technical manager for client and internal IP development projects at Entropy Technologies Bangalore since 2020. Now, I would like to welcome Dr. Nagaraju sir and request to take over the session. Thank you, sir.
Thank you, ma'am. Hello, everyone. Good evening. Indeed, thanks for heartwarming welcome and introduction. First of all, thanks for having in this event. Let me share my screen. Along with me, my colleague also be here, Ashwini. She is a design engineer. Could you please confirm my screen sharing is visible?
Yes, sir.
Yes. It is visible.
Great. Well, on behalf of Interpol Technology, we welcome you for this today's session. Next couple of minutes, we are going to have discussion on the topic given to us, parallel and pipeline architecture. The topic is very interesting. It's related to some extent computer architecture and VLSI. I'm very glad that I worked the same kind of earlier project. So I'll share my experience also. So without ado, we'll get started. Before getting into our actual topic, quickly just overview about our company. We are into 5 verticals: aerospace defense projects, automotive, industry equipment, training and academia. In training and academia, we are we are the Cadence distributor, and also you can see the Interpol is the first training certified partner in the worldwide. So our company have the legacy of 14 plus and hundreds of team members and corporate customers, and we have trained off and online. So, and also we can closely you can see the NCs. We have the best partner award in 2022. Majorly, we are into 5, around 4, of course. So this mechanical domain, electrical, electronics, and computer science. In electronics, VLSI, PCB, RF antenna are the strength of our specialization. We work closely with the giant companies in the world. Okay, you can see ANSYS, world known simulator for mechanical and various solutions, and Cadence, very well popular and state-of-art EDA tool for IC designing. Today we are going to be show some of the tools using this pipeline and parallelism architecture using Cadence tools. And down here you can see this Abhyanta is our training division, training arm of Interpol Technology, where we conduct the corporate trainings, and also it's a bridge between the academic and industry. We can means end of this session, if time allows, the activities of under Abhyanta we're going to show. And so let's come to our today's agenda. First, we're going to see it's like the title how little I'll demystified. So these are the first we're going to see how the computer architecture. Let me take pen. Okay. So and then discussion on the parallel and pipeline architectures. So here oral architecture we're going to analyze. Then the approaches to realize in hardware point of view as a designers and their challenges when doing the parallelism and pipelining, incorporating into the architecture. And that process, we are going to see one case study of 8-bit multiplier. And this majorly we're going to save are not readily available RTL code. I'll show and do the synthesis for the power.
Hello, sir.
Area. Yeah.
So voice is not audible, sir.
Oh.
It's audible, sir.
Okay. Sir, it is audible, sir.
Yeah,
it's audible.
Please, yeah. Could you please check, sir?
PPT and
yeah, well.
Everything is okay, fine.
Right.
Carry on,
sir.
Carry on.
Then fourth, we're going to see the EDA tools. What are the tools are helping to realize this architecture and optimization. And the last, I'll show you some of my research work where I used parallelism and pipelining techniques and architectural level. So in end, flag end will try to our level best to answer queries. Along with me, my technical team member, design engineer, Ashwini also be there. She also help. Okay. Well, we have to clear out. Okay. Well. Well, so first and foremost, if you see here, the modern systems are, we can at an abstraction, different abstraction level. All it start with the application apps related, then backed with the algorithms. So algorithms and then programming languages and then operating systems, virtual machines and all. Here it is the architecture location place. And then remaining here the VLSI architecture at the circuit level and RTL level. This is the exclusively like a physical device modeling physics, and it's then totally. So if you are see, this is the top to bottom approach layer we can see. And majorly our discussion today, we're going to see the instruction level architecture, computer architecture and micro architecture. Then we are realizing with the RTL and see the circuit how it is, whether parallel and pipeline architectures. Oh, it's quickly running, sorry. Okay, well, microarchitecture contains a few important major components like input, output, memory, data path, control. So we can see the data buses here. These are the buses, carries, address bus, control bus architectures, and it access like a reading and writing operations, and also data from input to output, the major activity. So using this bus architecture, we can realize our CPU at the single bus architecture, where we have only one single bus and all input output peripherals are connected. So the bus act maybe every once activity it is on active mode. If it is ALU happening, remaining others are waiting, are idle mode. So this is the single bus architecture, where you have the multiple bus architectures. You have the different, each and every bus have dedicatedly working for different peripherals. So obviously by seeing our architecturally that buses, if you have more buses, you have the more access and reading writing. So it is an advantage obviously. So let's come to the main, as we know, CPU are the major like components, like a register in instruction registers, control and ALU. Let's see in this how that operations and what is the deciding factor to be realizing our architecture, either pipeline or parallel or mixed type. Oh, I'm sorry, I'm using a PDF. Maybe it's quickly running your end. So, well, when you see the buses, as we seen earlier, buses, control bus, address, and this is the mapping, like a data address mapping, data mapping into the address. Now, let's come to, let's say I want to execute these are operations like a storing, arithmetic, and this each operations have obviously takes it in 100 nanoseconds first 150 and 33. So if you convert to the frequency domain, first operation loading and storing 10 megahertz, and arithmetic operation 20 megahertz and 30. So like these operations, once a single cycle or single cycle based CPU, each and every instruction per cycle. So obviously if it is running all this, it required 100 nanoseconds. Whereas if you have the multi-bus or multi-cycle architecture, one 3 cycles is required for loading and storing, remaining 2 and final 1 branching. So altogether, if you see within, like this is a 1 instruction, and it is taking, if you say all these 3 instructions added up in this one, it comes 33 nanosecond. So you can see when you have the single CPU 100 nanoseconds required, that means 10 megahertz of the speed. And when you have the multi-cycle, it's only required 33 nanosecond. The reason we are doing parallel operations, and we are taking advantage of independently each and every operations. That is the problem we have been solving. Like we are we are dividing the task, big task, and each task parallelly we are processing, and we are achieving the speed. So it may be we will, this is the major like a taking advantage of the different paths or different domains if we have. So let's, with this problem statement, let's move to what is the processor, like why we are optimizing and looking for high speed. So this one, if you see from last the inception onwards, CPU inception, so power and frequency exponentially increasing. Like if you are high speed, obviously it consume more power. So let's now come to architecture and hardware point of view. So I can want to be utilized parallelism and pipelining or mixed type. Which one is better suitable? So before that, let's see what is the ICs and how ICs are realizing. So it's a millions and billions of transistors in one IC. It's a majorly switching between logic 0 and 1. Now presently technology node 5 and 3 nanometer. So if you see here, this 1 nanometer means it's a gate length. So that if you are precisely say in the layman terms, human hair, if you cut 50,000 times, you'll reach that scale. So this is the scaling of the VLSI IC and gate length. So let's see how this will look. Means gate length nanometer. So now this is the fabrication technology. So for your information, I kept this slide. So presently, if you see, this one is CMOS. We have very popularly, and this one 28 nanometer, and of course some of the projects there. This is the gate actually. So this is the gate length. This is called nanometer. Here it is. Okay, and now presently in industry, almost all consumer electronics are fabricated with the FinFET, and it's a 40 nanometer and below technology. And recently GFF, gate all around technology, Samsung 2 nanometer, they were fabricated and they were successfully characterized. And this CNFET is under research, and few publications are there. So this is our present market for related fabrication of the transistors. Well, what is the main concerns when we are designing IC? So if you observed here, Intel different generations are here from i3 to i9 processor, and each processor you see the cores and threads, they are increasing. From i3 there are 4 cores only, now i9 10 cores. And the reason, well, what is the course and why they are taking this course and all, we'll see that whether it's a parallelism under or pipelining. And threads, they are like earlier we have seen different clock cycles, we have processed the instructions. So threads, are they using for thread for instruction level or data level? And also using from i3 to i9, they are increasing. And the main important here, speed and performance, power and performance. Let's see, from here to here, they are trying to achieve the speed. When i3 3.3 gigahertz, when i9 4.1 gigahertz. Obviously all we want to be execute high speed, all the applications we prefer high speed designs. And other hand, you can see this where power also increasing. So 65 watt, this one 512. So there is what is like it's a let's cross check, it's a milliwatt or what. So there is power is increasing from 65 to 512. So there is a power and performance inversely proportional. Like either you have to realize low power, when you are realizing low power, your performance have to be sacrificed, or you want to go for high performance design, you have to sacrifice for power. So that's why low power design or high performance. So but whereas area is proportional to the power. So if you have a number of less gates, obviously less transistors, power less, consume less. So power and area are proportional, whereas the performance inversional. So, and also if you see the generations from first to last, and there is a one trend, you can see the technology is shrinking, like 45 nanometer to 7 nanometer. So this is the like here major ingredients you can say for IC design or anything, we have to concern power, performance, area, and also abbreviated it is like a PPA. So all designers, they strive hard for optimizing or balancing between this one. So we can realize our ICs either prototyping on FPGA or semi-custom and digital or full custom. I'm not going to take because you all aware that. So here VLSI as a from specification to chip tape out. or chip level implementation. If you see, this is the architecture second. Okay, here it is the architectural. Once done architecture, we realize in the RTL code, and this is the gate level or circuit level netlist and physical design. We placing, or it's like a building or physical layout or analog, and then we verify with the DRC design rule checks. LVT was layout versus schematic, electric rule checks and all. Finally, fabrication and then packaging and testing. We deploying chip for products. So in this architecture, see, this is architecture at the top side. Majorly architecture side, there's so much optimization available for us as a designer or developer. So if this architecture is directly impact other stages, if it is not optimized any design architecture at this stage, remaining other stages will affect. So there is a so much optimization chances at the architecture. So that's where we can realize the architecture with the different strategies like pipeline and parallelism. Well, so this one is in detail about the semi-custom, and again this is the architecture at the top and realizing functional verification and formal verification. So we'll take as case study 8-bit and we'll see the different architecture: conventional, pipeline, parallel, and mixer type. 8-bit multiplier, and we'll see the RTL. I prepared RTL to show you demo on, and then functionally we will verify and formal verification coverage analysis, and I'll take you to the synthesis, where synthesizing we will generate PPA, power, performance, and area report. All the power, like a 3 ingredients, whatever we have discussed earlier slide. Power, majorly power, we'll try to cross check between the different architecture. Let's chip architecture. So this one is iteration, like a architecture we realize module and then clock reset and timing checks and review and verify, validate, and if it is there, and take feedback and changes made. And this is a iteration, and we'll try to optimize for block level, system level, IP level. So the basic idea, when we want to realize the parallelism, so let's say like we have processing of 4 different. Okay, so you can see the operations, 4 operations, and ABCDs are the color different data streams. So A1, A2 data stream and A3. So this different data stream, and it is start with the different P1 time A type, P2 B type, and C, like this. So what happened here? Parallel processing at the when A1 not dependent on B1, and I can be parallelly process P1 and P2 at the same time. So here you can see this is we are parallelly independent. So A1 is and this one B type in the P2 slot, and P3 is C type in P3 slot. Likewise, so here parallelly without any waiting for A value, B started and C started remaining all. So there is other way pipelining, where A type is starting and one latency, one clock cycle. Let's say like this is the one clock cycle. Each and every clock cycle it is happening. One clock cycle latency later, you have been starting with the A, B2. We are mixing here A, B, C. See here A type only we are processing and B are separated. But in the pipelining, we are mixing A2, B2 and C2. So that this is, you have like this for your A type, whereas pipeline parallelism straight. So the dependence on here, what happens here when you have this one at a time, at the 5th clock cycle you have all the data, so obviously throughput increases here, but here it increases the speed because only one clock delay cycle you have starting A2, and by that actually if you execute all this you may require as many as 20 clock cycles, but whereas you have been finishing at this clock cycle maximum 8, less than 8 clock cycle you are finishing your all your task. These are the data dependence, and also there's a pros and cons. If you want to be use parallelism, it should be no data dependence between the processors, like one process to another, as we said. And the pipelining will in inter processor communication, like A1 to A2, A3 and all. So let's parallelism. The reason why we need to use parallelism, the way back, if you see 79 to 2021, we keep on increasing speed of our processor, like 1 megahertz to 1 giga. Now presently 4 gigahertz is the highest speed, and we are exponentially increasing. Not so we want to be execute so many at the fast. So that reason we are dividing the task into sub blocks or subtask, and using the parallelism technique, and simultaneously or concurrently we are processing the data. So this is one example, as we all know, and Cadence uses this same in when you are executing your bigger design. Let's say like a CPU1, CPU2 or CPU3. This maybe you have seen, of course, and this will I'll show you. There is uh, you can find there is one app to see. I have using my Intel processor i5 details related CPU ID. I have opened this one. This app it shows here my Intel i5 processor details about this specification about my IC here, my system IC, 40 nanometer technology node and i5 processor. There is, you can see the cores are 2 cores and threading is happening 4. So that means if I want to execute a multi-threading, I can use 4 and 2 core. And also the moment if you can memory related full details, like at the top the speed of clock cycles, also you can see the clock cycle is varying. So two sometimes 2.8 gigahertz, 1.5 gigahertz minimum maximum. When more operations happens, it reach of full speed, like I mean full performance at the top speed. Like you can see this one, 2.4 gigahertz is the maximum speed it achieves. Okay, so like this core, same thing, like when our bigger designs comes, the moment like it divides CPU 0, CPU 1, CPU 3 and CPU like a CPU 0 to CPU 3. And I'll show you this one, the tools, Cadence tools, how it is uses this threading operation. um, okay, so let's open one tool. So let's, like, if I open my inverse tool, physical implementation tool, see here 8 CPUs are allowed for this current license. Means I'm using only 2 CPUs for this current license, because the tool uses different CPUs. Hope you are seeing here 8 CPUs you allowed for this current license. So the tools allows based on this license type, this kind of different CPUs, and it will come up and it will be divide the task and adding up final component. So this parallelism basically concurrent events, and it will compound and process, and it increases the speed actually. And also this parallelism will be have different levels. You can be realized program level, procedure or instruction level. Very well known, like RISC instruction level, people uses parallelism and pipelining techniques and all. So lower level you have uses shift register with the load, and the higher level you can use the different task or different block level identical blocks and all. And the same thing, like you can see one interesting, like first actually you can realize the parallelism under this pipelining you can also execute. Okay, so that means once you realize the instruction level parallelism, you can go for pipelining. That is called mixed type. Or whereas without parallelism, you can identically use for the pipelining also. So I mean threading is like we're going to see multi-thread parallelism, how it is hardware support multi-threading and multi-core architectures, and remaining this one how it is helping in present applications. Well, the parallelism, it can be hardware level. It's like in instruction level pipelining, you can or vector architecture type. The example are GPUs and all. Threading level and request as a, if you are coupling with the task different, we can realize with the hardware 4 different levels. So what are the things like we have to consider when you're doing a parallelism? operations should not be depend on each other. So then we can go for parallelism. You can go for circuit level. So when you have the multiple ways to be realize the cache memory, and you have the memory, and like a organization level, different instructions at the without independent of instructions you can execute, and system level for hardware without waiting for other input and output. So one example, like presently Intel processor, if you see here, from parallelism using from Intel Xeon processor, they uses one core, and then present Xeon processor with the Skylake 28 cores and threading 56. GPU architectures are one of the best example for data level parallelism. So they have intelligence CPU and GPU architectures. It help you to be realize the multiple things like graphic memories and video processing, all image processing. So let's see the this is one of the example. You can see NVIDIA Fermi processor. You have different restriction level at top and around 18 register type here, and then loading and storing in it, and interconnect network, and the local memory access, reading and writing memory access. So we are not going to getting to the issues when you are realizing this parallelism. So there are some challenges are there. It's not as simple as it is, but when you are mapping it, it is to be a partition mapping between the processors, and scheduling you need to be properly aligned, and the communication synchronizing between the input output data also we have to be taking care when we're doing the parallel processing. In the same, whatever we have discussed, advantage, disadvantage, majorly it will help you to run the simultaneously. So obviously it increase the throughput, and it can be scalable for different performance grade, and any resource sharing happens between the one processor to another processor. And then disadvantages, like it is complex increases when you are doing, and it required coordination between the different processors, and obviously to overhead if you are different processor, and it may be slowing down if more number of operations, and you need the a certain pipeline parallelism stages, like and once one point threshold later it may not be up, means you may not get the benefit of the parallelism. So I'll show that one of the publication paper, if you are more number of parallelism increases, what impacts you have to be okay. Now pipeline. So pipeline quite you can see this is a 4 segment stages, S1 to S4. You have register, intermediate registers are required to store, and the space, you can see the segment instructions are 9 within 9 clock cycles. You have executed more than one, each task has 6 type and 4 different. So 6 multiply the 4 different instructions we have executed within 9 clock cycle. And this is the calculations mathematically proving, like you can see 4-stage pipeline. If I want to be each stage taking 20 nanosecond and 100 tasks to be executed. So one task, if without pipeline, it required 80 nanosecond. So non-pipeline, it required n is the number of tasks and k is the stages, and the total, this is the TP is the propagation time, and total if you see 8000 nanoseconds required. Whereas the pipeline stages, you required only 2060 nanoseconds. So now you see the 8000 by 2060, 3 times, around 4 times. 4 times you have speed up the design. So using the, so here you can see the P1, P2 are the stages are, and you require the, what is the disadvantage here? You require the registers to your pipeline registers, but if you are bare with that hardware overhead, registers are, then you can be go for this pipeline stages. Okay, so of course that is not a major, and we'll see one 8-bit multiplier when we use the pipeline and parallelism, what area, how much area it is decreasing or increasing. Well, I hope you are with me. I'm just cross checking the connection. Could you please confirm?
Yes, sir. Yes, sir.
Yeah,
Yes,
thank
sir.
you. Well, I hope this speed is okay when we, with our discussions. Maybe if I'm going very fast, kindly stop me, and free feel to stop me.
Yeah. It little bit more slowly now, it is very useful to us, sir.
Oh, sure, sir. Sure.
Little bit more slowly, sir.
Slow, sure, sir. Sure.
Okay.
Well, The pipeline, let's say I want to be execute each and every color have instructions. So each it takes one clock cycle. So you can see total nine clock cycle, only nine instructions. Each nine clock cycle, nine instructions. Whereas instruction level, if your pipeline at this one pipeline, it take all the fetch. It fetches like this four in one, and the next one you are aligning to the immediately next clock cycle without delaying, or sometimes it is required, of course it is immediately started here, and then two clock cycles here latents later you have finished your. So normally only 1.5 instructions are required nine clock cycle, whereas till this clock 7 you have executed total number of 4 instructions. So this is we are handling, and with just like a divide and rule kind of thing, slowly just properly aligning, and so that we can get the benefit of end of instructions. This later you can be speeding up all the operations here. Next, so pipeline, where we keep the pipeline stages. Without pipeline or single stage, there is, see, each and every CPU or some blocks, sub blocks later, instruction memory later, there is no immediately it is connected to the register block here, ALU block here, data memory access, instruction memory, and then add. So there is no pipeline, I mean registers here. So when you want to use the pipelining, so we need to be uh, where we have to be just we have to be identify the pipeline stages, and we have to keep the registers. These are the registers, 4-stage pipeline. So each stage takes one clock cycle execution of this. So sometimes this all operations not happen in one clock cycle, then you have the timing issues, maybe setup or hold violations, and between the register to reg. So there is a called STA, static timing analysis engineers. They check between the register to register whether all this one clock cycle means one rising and falling, like this. So when at the rising edge of, when we writing RTL code, at the rising edge of the clock, one clock period, let's say like one clock period, all this happens between this, all these stages should be complete, or it, whether it is completing or not, we will evaluate with the static timing analysis. And we all know that data path, if combinational logic is more delay or taking more delay, we have to optimize. Okay, so there you can be optimized either RTL level, architectural level, or you can split it one block operation into other block. So it is not a thumb rule that we can have to only use 4 stages and 5 stages and all, but it is a different designers, they realize different. I just a few days back I searched researched something risk processor based. Some people all they started with the 2-stage pipeline to 10 or 15 stage pipeline. So the more pipeline stages, there is a hazards are there, but we are not going to in that details. Hazards means data hazards, instruction hazards, control, or there are some between the block to one register to another, one stage to another stage, some data corruption happens. So we have to take care. That is also be we are challenging for a designers, those who are realizing with the pipeline stages. Now we'll see the case study use case here, 8-bit multiplier. So the moment when you want to do the multiplier of 4 input here, of course for simplicity we'll take the 2 input 8-bit multiplier. So first one is multiplicand and multiplier, and the majorly hardware engineers they trouble with this partial data or partial product to store, or these to be stored in the intermediate registers between one register to another when you want to be parallelism. So finally product, you have to be align all these values. And the moment that any of the design or any of the system, the path which takes the more delay or more, so each and every here full adder, off adder there, and gate. So from the way from this path to enter this, it traveling this path, we can also cadence tools will help you to see the path of the critical path. So the path which taking the more delay, that is the deciding factor for operating frequency of your design. So it is taking 2 nanosecond to 2 nanosecond. If you convert into okay, propagation delay it is, so altogether from this path to each and every cell it counts, and cumulative value, that's the deciding. So if you are optimizing this critical path, you are increasing the speed of the design, obviously. So if in common, why we use as pipeline to improve the performance and also increase the throughput, it help you to increase the throughput and reduce the latency, and it allows the different stages and computing and multiple tasks, and it performs simultaneously. And this the parallelism, okay, of course, parallelism sentence earlier it is, and it is resource utilization, higher clock frequencies, it helps. Okay. So because this parallelism, why we kept here, because inherently pipeline is part of the parallelism. That's how we have added here. Okay, now the registers where we have to, and deciding factors here. So this is the place where pipeline registers are kept, and this is the mathematically we are evaluating the multiplying between the input to the output, how that output increasing. You can, if you see the registers 1 by 4 of uh, propagation delay, and so instead of this 1 by 8, it takes 1 by 4th. So if you are not pipeline, you have to consider from here to here, whereas like, let me take pen. So this is the 8 propagation delays you have to take without pipeline, but if you take pipeline only, you have to take these stages. So the latency and throughput increases, as we said, performance matrix for, and the latencies, you can see this is the ideal state. When you are pipelining stage, you can see this is fx is waiting and gx is waiting. When we do the simulation, we can see this. When we do the pipelining of this multiplier, we can see the ideal state of the other values. Well, if you see one pipelining calculations here, so from input x to product of x output, so each there are two paths here, one path here and another path here, 15 and 25. You can see total here, maximum path is this one, 20 and 25. So L 45, and if you are 1 by 45 is the time value. So assuming if you have registers kept here in between two registers here, and the tool will consider this one is the timing clock 25. So 2 multiply with 25, 50, and then t is 1 by half t clk 25. So you can see this, how this is the changes, adding assumptions of t value 1 by 45 and all. So this will help, actually it is handling between the registers, between the pipeline stages, and it is helping data to be processed smoothly between the different stages. Again, this one pipeline diagram for a cycle wise pipeline stages, realizing, of course, this how we discussed. Now, how we realize is something like a pipelining multiplier with the like a multiplications and all operations. So if you use multiplicand operand, so you can unsigned, you have A and B are the 8-bit or 10-bit, and you can multiply with the unsigned. So signed, like signed also almost register why it is going to be changes, declarations and all. So pipeline registers that without pipeline, you have to assign G value to Y. Let me take pen here. So you can see this is the without pipeline, with the pipeline stage, and without pipeline, that Y value, this value immediately assigned to this value. So you can see this is the assigned statement, and then this pixel data value assigning this cy value. So these two assign statements directly we are logic for y and pixel, and this is your RTL going to be like this. There is directly your g value assigning to y and c value assigning to the pixel in always at the any changes rising edge of the clock. When you use the here registers, this clock registers, and you have uses first always at the positive edge of the clock, and then we are assigning either intermediate states g of x to y and c of x to y, because this is the the registers, it will remember, means it will store your intermediate stage of y2. So this is y2. So here only y, here y2, we are not okay. Let me clear off. So here this is the y2 here. So this is the y, this value we are assigning here jx, whereas this is directly y, and this is the y2 of c2, this is directly c value. So that is the data, that's the pipeline stages. And the code, obviously this is the, if you have positive, this is the RTL code for pipeline stages, and whereas non-pipeline stages. And without pipeline, a simple RTL 4-bit input and 32-bit each one. If you see here design majorly, you can see stage 1 directly we are assigning with this stages, assigning these inputs, input 1 to a0 to a1, input 1, input 2, input 3, like that. So we are assigning each, first one is multiplying, then assigning to the stage 1 result, then 2 are assigning. So you have first multiplication, like this one first, then another set of multiplication, then adding up here. Okay, so addition operations. So this one is just like multiplying differently and adding up here output. So with pipeline, if I want to use pipeline stage for this same design, I have to take intermediate steps here, registers. You can see stage pipeline, then I'm dividing with the different operations and assigning to here and synchronizing with the rising edge of the clock. So limitations, of course, this is the instruction level. When we are one instruction, let's say like this register value immediately without executing this is not going to be take place. So that time, so it has dependency, so that we have to be consider when we are, so this register value depends on here the before these operations. So this is depends on these three operations. So that where we have to be, either we have to realize this operation at this place, or this one at here. So we have to decide the instructions at what time, dependency, based on dependency, and we have to taking the decision to be execute the pipeline stages. And when come to disadvantage and advantages, pros and cons for pipeline stages, increase the throughput and resources, and execution time also reduces scalability, increase the speed of the design, and it will be repetitive task, it will be demystifies, and it will be keep it very simple to handle for the especially ST engineers handling these pipeline stages and all. Of course this evaluation is required, and instruction line parallelism, we can use that. If you ask the pipeline parallelism instruction also, you can utilize inherently. So disadvantage pipeline stages are, you have the hazards, prone to hazards, and latence, you have to and power consumption is more, and the area requirement because of the registers and all. Remaining all, hope you. So what are some of the i7 processor? If you see, this is their architectures and all, and this is the multi-thread, like a parallel, different CPUs. This is the die of their the cores are 4 cores are here, and this is how accessing of the above level die level graphic processor with the different other cores. Now, what are the cadence tools, how they are helping? So now let's see this cadence tools like a circuit level, and this is the physical design level. Here it is the circuit schematic layout, and this is the physical verification circuit, and this is the digital genus synthesis and inverse, and mixed RF and RF and microwave design also be cadence supports. Okay, so we'll now we'll see the demo of that 8-bit multiplier. For this, we are going to see majorly. I'll take it out this RTL code of 8-bit, 2 input, each one 8-bit. So using functional simulator with intensive and synthesis with the genus tool. We uses PPA, power performance of. We are analyzed at this, and this one I will readily available layout of Innovos based physical implementation of one design. I'll show you. Okay, now we'll quickly jump into the demo of that design. Let's minimize. Okay, well, let's execute. For this, to show this example, so one conventional multiplier. So this is a multiplier, you can see conventionally version 1, version 2 parallel pipeline. I mean, so then third one is pipelined, and fourth one is mixed type. Each and all these 4 version will analyze the power component or timing also both, but for Gandhi we can, and we uses the here technology node 7 nanometer. So 7 nanometer technology files are available here. So I'm using 7 nanometer implementation of this first conventionally. So here conventionally input, so I'll show you the RTL code quickly too. So I'm taking this A, B as the 8 input, 8-bit, and then product is the 16-bit. Okay, and then the conventionally you can have the partial, each and every right shift and left shift uses, and then you have been multiplying, adding. This is adding partial products with the appropriate shifting, and then partial product generation with this command. So total, like you can see the 24 lines of design, and to verify this, we have test bench are kept it ready. So we are testing unit under test, it is called here conventional multiplier, and then we are first a double a hexadecimal value of double a double b after 10 nanosecond ff, and let's see this all the products, and once it is now code is ready. So now let's invoke our simulation and see launch. So I'm creating work directory here. At this simulation stage, technology fuzz is not required. Now RTL code, the same RTL code, you can see this is the edit view, same RTL code. Okay, select this, and first we have to syntax check, verify compilation. So it is successfully compiled. I kept is very without error free, means error free, because if you have any errors to debug in front of you, it's take time. That's why I just kept it ready. And test bench also ready. Of course, now once this completed compiler, RTL compilation as per IEEE standard, Verila coding and all, now elaboration is ready. Now this is the elaboration stage. If you click on elaborate, if you have a bigger design, it will build the hierarchy. Test bench code is also we have to elaborate. Once this elaboration also complete, now third stage is simulation. So you can select the test bench. I'm only selecting test bench here and sending to the simulator. So whatever the test bench cases, stimulus, whatever we have given, it will come up with the unit under test results and compiled. So now select this. Now at the initial stage, all are unknown values, X values. And now select it. This is the send to simulation waveform window, sim vision. Now there is a play button here, icon here. You can click on it at once. It is so now the design is executed without error. So now I can let me convert this to digital. So digital format. Radix is now presently hexadecimal. Now we can decimal. Okay. So now see here clearly there is a at the without any here there is no clock signal I have used, so it's like a purely combinational. So at first 0th clock cycle, it's a value 170 and b value 187. It is calculated this value multiplied 31,790, and the second after 10 nanosecond as per my test bench 10 nanosecond 25 multiplied with 1. So 2 cases only have covered here. So this is perfectly working, and we can see also elaboration. If you click on this, how it is architecturally when you want to see this unit under test. So if you double click on it, unit under, so you can see there are so many that operations, whatever operations we have added, addition operation here, partial in between the input to output, a different architecture you can see here. So this is conventionally different architecture than pipeline and parallelism. So let me take this screenshot of this to show you other once the pipeline stages works. Okay. Okay. Maybe you can remember. So this is the like this different architecture, like a round multiplication and addition operation for this conventional. Now we have verified this one, and now at the same time uh, I will execute. If I execute the same design with the pipe parallelism first, next we will go for parallelism, same design. So this design, so using just assign product to here, and then I'm just taking the a value, b value, and assigning to this product without any assign statement, and then test bench here. Okay, test bench is the same here, a b values are multiplying. Okay, and I'm calling the parallel unit under test. Now let's simulate this also and see launch new. So there is a tool called Exilium. It uses multi-threading of, if you have this is a only 20 to 30 lines of code, that's why quickly it is simulating and executing the simulation results. But if a bigger design, it take the multi-threading of this one, and now it is partially elaborated, and then test bench. Now we can, we'll see first results, and then we'll see the architecture, how it is that look like. If double click on double click, okay, so now select the test bench. Inside the test bench, unit under test, you can see here, this is actually our design, test bench, and go for simulation window. Let's execute. So this is also working as per. So if you are convert this to radix value, so it's 255 multiply with, is a here 10 multiply with 11, 110, and 255 multiply with 1, so it's working perfectly. Now we'll see the code based architecture, how it is look like, the tool how inferred. This is unit under test. Now we can see one product multiplied of this one. Earlier you have so many like this multiplied, and this one is you may be that technology files based multiplier or Mac based or multiply accumulate added. So but it is not in details of this multiplier architecture, it not shows, but it shows the number of, if when you do the synthesis between the conventional and parallelism, you see the changes any hardware level or type of netlist it has inferred and all. Now we'll go for the third version, pipelining. If I use the same design for pipelining, and we'll first functionally verify, and we'll see the architecture. Let's go for third version pipeline, and this is the article code of pipeline. Now you can see this is the registers, intermediate registers we have taken, and we are using intermediate registers and the positive rising edge of the clock, and assigning to the product here, additioning of that all, and the test bench is here ready. So let's, sorry, we need not required. And see launch new simulator. Well, select this design, compile it as same like earlier, test bench also compile it, and then elaborate. Downside, you can see the process development of that. Now verify. First we will verify the functionality. So yeah, now select this test and send to simulator. Now there is one new component here, clock, because the pipeline stages, every register have to be synchronized, right? All rising edge of the clock. That's why we have used here. Earlier we didn't use. So now you can see there is some latency or delay here, ideal state. So there's some block, the pipeline stages. Due to the pipeline stages, your output is delaying here. Let's all are convert into binary all. Okay, select. So at 0 till 10 nanosecond, it's essentially 0. So you can see the clock is rising edge, even the rising edge output and input are not. So next clock rising edge is happened at here. So by the time your A value 10 and B value 11, it is considered, but immediately not delivered, because this is the processing, your registers delays. So it is appeared the next rising edge of the clock of your value. Earlier, when you use the parallelism, immediately it is appeared after this one. You may be observed the changes. Now at the pipeline stages, it required the one clock cycle, almost from low to high and then low. So 1.5 clock cycle later, next clock cycle later. So here one clock cycle, another second clock cycle later, it is processing. The same way here, this is appeared, but it is at 0, means fall clock, lower clock cycle here. Rising, this is the fall, and rising clock cycle. Now it is collecting this 25 to 255 one, now calculating, and it is appearing at the next clock cycle. So this is due to the parallelism in your code. And then if you are see the architecture, how it is that inferred at the, now you can see that changes compared to the conventional and parallel and parallelism and pipeline. So now you can see this is a registered D flip-flop, and you have the intermediate registers or flip-flops are here, register type flip-flops, and then shift operations are here. This is how the date based on your architecture. Now, how do we know that which is a better one? Then we have to go for power performance. So that is the synthesis stage. And also mixed also be there. Mixed I'm not going, because mixed is a fourth version. It is mixing between higher and I mean, so it's a designers have to decide whether you have to go pipeline or parallelism based on their requirement or mixed type. Some people they go for deep pipeline or massively pipeline, and also some they are system level they use as pipeline. And I show that for some of the publications of ours, we have system level used parallelism and the cell level used pipelining stages and all. So synthesis, now we'll go for synthesis. We have 7 nanometer technology node outside of our folder. So here it is the folder. I'm just generating power area report. See this. Now we'll gather the each and every version's power and timing report majorly. But timing means area, power and area reports, and we'll compare. Sourcing my RTL code located in the script. So, and then, so this synthesis engine now taking 7 nanometer technology node, and it is mapping with the like a first transform technology transform elaborate, and then it is like optimizing also, so mapping optimizing. So you can each and every line you can see that the editor, like, so some of the places you can see the tool uses multi-threading. So it is the design is threading with the different other mapping time. So okay, so if you open the log file, you can see the threading term. See, there are configured 4 threads are using here, and then this is a 4th thread, and remaining, if a bigger design, it takes multi threads. Genus tool, it inherently takes the multi-threading. Now done. Synthesis after, you can see my GUI, graphical user interface, we can open and let's see. And the power reports, everything is in the folder. So this is our conventional multiplier 8-bit. So if let's us see the schematic in the main window. So this is the schematic of your technology, 7 nanometer technology mapping. So that is earlier one RTL elaboration, but this one schematic of yours mapping with the 7 nanometer, and full details if you want to see what are the cells inside and all. Let's you can see the power report here. So this is the leakage power, this much nanowatt, and internal net switching power, and also number of cells. So like here the report in the folder, I prepared the script to generate power report. This is the power report. So it is in watts here. Power report, it is watt here, and then leakage component, internal switching, and total power. Total power is this one. So it's like a 1.07, or if you convert this one, 10, so it's like either 107 milliwatt, or no, it's like micro. Okay, point one, if you go to the point now, macro watt, or 10 power minus 6, right? 10 power minus 6 or 10 power minus 9 nanowatt. Okay, and 10 power minus 3 milliwatt. Okay, so that we can convert and we can check it out. And it is to observe between these two. Let's see the one common thing, number of cells, like cells, you can see the over netlist area. Okay, total cells for conventional is required 200, and 339 is the micrometer, I guess, macrometer. So this we have to see in the unit, type of unit in the technology files. 200, you can remember 200 for conventional, and each and see AND gate are 6 are inferred, and full adders are 32 inferred, and this NAND gate are 58 inferred, and then XOR gates are like this many altogether, areas and all. And so this, so now we'll go for synthesis of here. So I have kept ready the same process. Now for number of cells here generated, so parallel cells here, now you can see there is a 2 increased, only 2 increased, and this is a slightly changed area increase. When you use this parallelism, only 2 cells are increased, almost same like conventional here. And then we'll go for we'll see the pipeline based synthesis. Okay, here number of cells when you use as pipeline. So it decreased drastically, 134. So pipeline uses decrease the your area. Total number of cells are decreased. Obviously, power also decreased, and it increased the power, means the speed of the operations. Number of cells are less. Obviously, each cell's taking less number of, okay, optimization, and also it impact your settings, like the constraints, based on constraints, and also and timing. You can see we when we ask this, it's a positive side. Slack is 236 picoseconds, and when we run this 1 gigahertz speed, it is running 230. Still, 236 is positive, so there's no issues at the clock side. And if you want to see here the timing paths, like where we have seen earlier, critical path to see. Let me show you here. When we uses genus, let's see the critical path of at this stage. Well, almost we have come to the flag end of our discussions. Let's see remaining reports. Like where earlier we have seen the timing path or critical path. I'll take you to that slide. Yeah, this is the path. Same path we'll try to analyze at synthesis stage here. So you can see there is a one one thing you can also notice here, multi-threading technology mapping. So this genus uses 4 threads of 4 licensed CPUs. Out of 4, as we've seen this, right, is this one. It's a 4 threads are using at this stage and at top, because to execute at earliest these designs. So once this design completed, now we can see GUI show. And then the pipelining architecture, earlier we have seen conventional, right? Now we'll see the pipeline architecture of 134 standard cells. See, this is the architecture. Totally different cells are inferred. And timing, let's see the paths. So there are several paths are here. The path which taking more less slack, that is the critical path. So if you click on this, so this here in this path, these are the cells, and then path is cells is not schematic wise not showing. In Innovos it shows number of paths. So in this path, these are the cells, each cell delay, and it is sum. Okay, so clock to a value here. Okay, this all the different cells. Okay, so like this, each and every path we can see the slack values and all. Now with this note, like we can be there are some publications you can see. There are one microelectronic and elsewhere, I think this is a microelectronic journal. Okay, engineering science, and okay, this one is the one of the journal. They implemented this power delay and power topology, different multiplier topologies. Of course, this is a circuit level, but in the end they compared with the different topologies with the power and delay component. See here, they have different voltage levels. They use CMOS technology, and they identified the delays, all the standard cells delays and power consumption and power product. And also we as a part of our projects, so initially I just utilized that one paper. This is our research paper. So in 2021 it is published. So it was published 2021. Here we have used high throughput parallelism technique for throughput increasing and area efficiently decreasing. And then if you see the let me take the pen too. So 5 clock input symbols we have processed parallelly, and this is the actual process our data should be, and the serial processing of the bins here. And then here there is a bottlenecks. It is dependent one on upon. So we are using one core. So this is a one entire block for one core, and this one we replicated with few different cores. Like this is a top level side. So 5 SEs at a time here, and then 5 BN different cores are working here, and we are parallel input parallel output registers, serial inputs parallel output registers. So this is the area we this is the area we propose, like a registers. With the help of the registers, and we have released the 5 different, each are different independently work, each and every core. So this is a one core. If you assume that this is the entire one unit, so the same one we are 5 times called, like here this is the 5 different cores, each core 5 different, and parallelly it executes the parallelly each and every instructions. And this is the parallelism used in the paper 3. And another paper we use the pipelining. So this is the okay, this is also here also parallelism, sorry. So this is also some kind of same design on one more SCI journal. This, so here instead of what we have here, there is only 5 cores. Okay, And we have experimented with, instead of 5, there are increased number of cores. So in the second paper, if you see here, total cores are now till 6 cores. So increasing one core, one to 6 cores. So what happened here, the changes, observations. So if we keep on increasing 1 to 6 cores, impact is like there is a, here it is the analysis. We can take up this slide. Okay. Now, if you look here, so there is a limitation for parallelism also. So the moment when you take from this different cores here, 6 cores, okay, from one core to one, so this is the maximum frequency. So it is attained the first core highest frequency. So when second core frequency is decreased like this, and third core again decreased, fourth core, now sixth core, your speed is decreased. But throughput, you can see here, at initially one core less throughput, second increased, and keep on increasing. At the fifth core, it is increased throughput. Okay, so there is a something like here. At this point, I can go for my throughput and speed, but remaining thing I have to sacrifice. If I want to high throughput, I have to sacrifice speed. So you can see this side is maximum operating frequency. This is a throughput values 1.3 and all. Okay. So like here 200 to 800 megahertz increasing. Like you see, this one is here. You have to see this is, so 800 to 200 it is fall down for core 1 to core 6 speed, whereas throughput is 0.7 to 1.3, it is increased. So it's now inversionally some point later, at this point or some point, this is the in touching, like you can see here, at this point later, the output and frequency are inversely proposing. So at this, you can take only, for my design, only two stage parallelism, or two stages only I can use, two cores maximum. If I go more cores, I have to go for high throughput. But if I want to speed and also throughput, only two cores only I have to be utilized. I have to get the best results. And other third paper, we mixed both these two. Here you can see the mixed parallel pipeline, and one more ICI journal. It has been in the review for last 1 year. So it's a VLSI integration. I can't show that, but it's under review for last 2 days. There also we used mixed parallel and pipeline architectures. You can see this Springer. Here, this is the pipeline stages. 3-stage pipeline we utilized here, and parallelism. So here parallelism is used here at this stage. So above one this is the parallelism above one pipeline stages. Okay, architecture elements. This is actually parallelism here, and pipeline in the next stage. This one is the pipeline. So this is how we can implement our hardware. So with this note, I come to the end of our discussions today. Thank you so much for giving this opportunity. I hope this discussion is informative and useful. Okay, final thing, I just want to show you the physical layout. Let me connect my server. Before that, if you have anybody have any questions, please. If you feel now, floor is open for question and answer. For better, for better communication, I kept everything is English. So నాకు మనం అంటే తెలుగు వాళ్ళు కూడా మాట్లాడుకోవచ్చు, బట్ నేను అలా ఫ్లోలో వెళ్ళిపోయాను. ఫైన్, మేడం, ఓవర్ టు యూ, మేడం.
Yes, sir. So participant, is there any queries? You can raise it in the chat box. Anil sir, please check with the chat box.
Ma'am, as of now, no questions, ma'am.
Okay.
Hmm.
So forum is open to all the participants. You can unmute and you can have your query to the resource person. Sir, I think there is no query from the participants, sir.
Uh, Sir, good evening,
Sir,
sir.
please, sir, please,
Yeah,
carry on, sir.
your insight was very nice, sir. The excellent presentation. But I have a small clarification, sir. Sir, shall you write? Suppose shall we write in the paper in parallel processing? Sir has to guide us. This is it possible to guide us through WhatsApp or mail?
Sure, sir. Sure. Always welcome, sir. Definitely. In email is one of the best way communication because phone wise
Yeah,
we
yeah,
may
sir.
have. Sure, sir.
Yeah,
We'll
sir.
leave
So,
our emails.
so if you don't mind, you share your mail ID, sir.
Sure, sure, sure.
Okay.
So we have one common, our designers, like our team, design engineers,
Yeah,
and we
in that
yeah.
team you have to include us, sir. Then it is also very useful to us.
So I dropped here in the chat box. Hope all you can see.
Oh, good, sir. Cadence, like.
Yeah, cadence underscore support at ntipple.com, sir.
Okay, fine, sir. Keep it. Wait a minute. Just you are not.
So, sir, final before that, I just would like to show our Abhyanta activities. So we have delivered the same, some of the, every week we are delivering for open sessions for different universities across India and worldwide. So there is a name
Oh,
called University Tech Bytes. So
okay,
this,
sir.
I think,
Okay.
University Tech Bytes, we are delivering each and every week one exercise with the front end and back end, all basically the tool flows like Innovos, Qantas. You can see there are more than
Okay.
7 to 8 tools we give the demo. Our team used to give from every Friday, 1:30 to 2
Okay, good,
p.m.
sir.
You have to register
132.
one time. Yeah, once you register you will get freely. So every sessions you can register, means every one time if you registered, every week you get this type of title of
Okay,
that,
sir.
sometimes analog, mixed and all.
Sir,
So these are the
shall you,
previous.
shall you send the link, sir?
Yeah,
Registration
sure,
link.
sure, sir. YouTube sessions. So you can also, like last time we have delivered here 32-bit multiplier. So there you can find the layout view. I could not able to connect my hard server here for physical design tool to show, but you can find in the uh, like here I'll show you that physical design verification. The same whatever we discussed the multiplier, um, that data can.
Sir, actually you are concentrating only low power or
Yeah, balancing. So balancing.
timing,
So this is,
timing
yeah,
analysis or other aspects also you are concentrating.
balance, sir, between the power and so some of the papers title itself it says throughput. Here it is the throughput. Some performance. So it's like a
Super,
title
sir. Super.
throughput and area efficient power
This only
power.
this only you lastly publish, yes?
Yeah, recently.
Good, sir.
And this layout related to this multiplayer pipeline multiplayer you can find in this video. So if you want to show recorded video, I can show. But
Sir, whether we have to implement 64-bit.
yes. You can go for higher, and it's depend on what type of like requirement and all. So It will show the
Okay.
layout view of our.
Okay, sir. We will join your session. You will give the valuable insights about how to write the paper based on the parallel processing and all. As
Most
what you used, that you have to convey to us, sir. Okay,
sure,
now
sure,
we will register in this link. Okay.
sure, sir.
Thank you for your sharing, sir.
Thank you so much, sir. I hope this discussion helpful, and wish you all the best for remaining program, and looking forward. And thank you all.
Thank you so much, sir. Dr. T. Anil Kumar, I'm requesting you to give concluding remarks of the session.
Ma'am, there is one question I think in chat box, sir.
Okay.
Then please
Using
continue,
of both parallel and pipeline design, what about switching delay if increase? How to speed up, sir?
Okay, so switching happening at the RTL, like if you are unnecessarily writing RTL means stages like a number of instructions like a code level, RTL level. If you are unnecessarily let's say like always at the positive edge of the clock, even in that begin to end, if not necessarily, it will switches. So it increases. So at the RTL stage, you have to rewrite. You have to come up with the RTL, fine-tuned RTL to decrease the switching delay. I hope you are understood.
Thank you, sir. Thank you, sir. Ma'am, I think more questions in the chat box also.
You continue, sir.
Yes, ma'am. Good evening, everyone. It is my privilege to propose the vote of thanks for today's insightful session on parallel and pipeline architectures in Cadence. On behalf of Department of ECE, GMRIT, we extend our heartfelt gratitude to our distinguished speaker, Dr. M. Nagaraj sir, from Entpool Technologies for the enlightening presentation. Your deep dive into the concepts of parallelism and pipelining, coupled with practical insights into Cadence tools, has been truly inspiring. You have simplified a complex topic with remarkable clarity and precision, providing us with a deeper understanding of its practical applications in architecture design and optimization. Your expertise in this domain and your ability to connect theory with real-world scenarios have given us valuable perspectives to enhance our knowledge and skills. Especially thanks to our enthusiastic participants for their engagement and thoughtful questions, which enriched today's discussion. As we conclude this session, let us take forward the learnings shared by Dr. M. Nagaraj sir and apply them to innovate and excel in our endeavors. Thank you once again, Dr. Nagaraj sir, for your time and for sharing your expertise with us. Thank you, everyone.
Thank you, sir. We look forward for your collaboration and future, definitely.
Thank you, sir. Thank you.
Thank you all the participants for your time.
Thank you so much, sir.
Thank you, sir. Thank you, sir.
So may I leave, ma'am? So can I? Now I.
Thank you, sir. Thank you, sir.
So we'll start our next session. So I think our guest has already joined in the link. Bhavna garu join ayyaru kada sir? Hello.
Yes, ma'am. Yes, ma'am.
Charan sir has joined. No. So shall we start the session, sir?
Yeah, I'm audible and visible. Good evening, everyone.
Yeah,
Hello.
good evening. Yeah. So Revati ma'am, we can start it.
Okay, ma'am. Good evening, sir. On behalf of the ECE department, I welcome you, sir.
Thank you.
Good evening to all. It's my pleasure to introduce today's resource person, Mr. Sai Charan. Mr. Sai Charan currently working as a senior engineer in analog design and mixed signal IC design at Samsung Semiconductor India Research in Bangalore. His role is the development of innovative semiconductor solutions, focusing on designing high performance analog and mixed signal integrated circuits. He completed his MTech degree from the Indian Institute of Technology, Kharagpur. He completed his BTech from CMR Institute of Technology, Hyderabad. His professional interests revolve around analog IC design, mixed signal IC design, and RFIC design. These areas excited him to play a crucial role in enabling cutting-edge technologies such as wireless communication, IoT, and high-speed data transmission. Now, I would like to welcome Mr. Sai Charan sir and request to take over the session. Thank you, sir.
Thank you, ma'am, for brief introduction on me. And hello, all. So, welcome you all to this session. And can you please give me control to share my screen?
Yes, sir.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Given, sir. You can
Yeah.
share the
Thank you. Thank you, sir.
presentation.
Yeah. Yeah. Hope my screen is visible now.
Yes, sir. Perfectly agreed, sir.
Yes,
Yeah.
sir. Yes,
Thank
sir.
you. Thank you very much. So, as this session is on VLSA design for secure communication systems, today's agenda for this session is in this way. So I'll first walk through. So am I audible to all? Sorry for I just need
Yes,
to
sir. Yes,
confirm.
sir.
Yes, sir.
Audible.
You're audible.
Yeah, thank you. So today's agenda for this session would be in this way, and I'll first like to walk you through some basic introduction and type of hardware attacks that are possible. And next we'll be seeing the role of VLSI in these, I mean, design for secure communication systems. And I mean, how can we get rid of these attacks, or how can we protect our systems from these attacks? So basically, starting, so going through the introduction, this is, I'll make a slideshow. Yeah. So this is just a brief introduction, like why do we need secure systems all over the world? So there has been a lot of demand in IoT systems, and the demand has risen very much that now everything we are connected through IoT devices, or say financial transactions, or whether military communication systems. So everything is connected right now, and the technology has been grown in such a way that with the pros, there are also cons, like say security part. So there has been issues like eavesdropping in the sense we can listen phone tap, like you have listened to the phone tapping, right, in such a way, so we can listen to the other communication as well, so which happened during World War I. And other than that, signal interception, side channel attacks. So we'll see what is meant by side channel attack also. So as a part of our VLSI design, which integrates some billions of transistors on a single chip. So this plays a good role in building secure communication systems. Like even digital design is about implementing encryption algorithms. There has been a huge part of analog circuits. So which we'll see in later in this presentation. Like these analog designs, we can through this analog design we can do a uh, circuit level implementation for signal integrity, security key generation, and safeguard against physical attacks. So to be brief, hardware security is just a vulnerability protection, um, which we need for secure communication systems. Like first, before going to the next slide, I would like to introduce some brief technical terms, like which we use in hardware security part. So like cryptography, it is just masking the information. That's it. And secret key means the piece of data which we use while encrypting or decrypting the process. So well, like there is a next term called ciphers. So cipher means an algorithm or a set of rules that is used to perform this encryption or decryption. And there is a block cipher. So AES means advanced encryption system. There may be a 128 bits or 256 bits also. So the type of cipher that encrypts the data in fixed size blocks is known as a block cipher. And going through the next one, types of hardware attacks. So in this, there are wide varieties of attacks like side channel attack. So what happens is that if there is a software attack, that is through breaking your firewall of the system. But how can one perform a hardware attack? So say now from your system, or say whenever we use a example, if I take a card, a credit card or debit card, so in that there will be a small chip. So that chip also emits electro EM waves and etc. for its functioning, right? Electromagnetic waves, and that chip is operating on the transistors itself. So there will be a power consumption. So now what happens is that these attackers gain information from this part, like the physical implementation of the system. So rather than exploiting the software vulnerabilities, and they will analyze that information and get that secret key or encrypted the encryption which we have done to secure our system. That we'll see one of the attack in detail. So I'll go through that attack in detail. And before that, these are some of the attacks like fault injection attacks, timing attacks, and power attack. So in general, what happens is that in power attack, there are two types of power attacks again, simple power attack and differential power attack. But what happens is they connect some device. Through the device, they analyze that power information, I mean power analysis, power versus time, and through that information reveal the secret bits. Like there is 128-bit AES which I have said. So those 128 bits, if it is revealed, then your information is lost. So what happens is on the right side, on my right side, if you see, there is input cipher text. Cipher text in the mean, it is an encrypted one. So what they will do is through the side channel information like power consumption or electromagnetic radiation, or through injection of faults, or through sound also, they'll do side channel analysis. And through that, then they'll get an plain text, which is the secret information. So that means our system is compromised. So this one I would like to explain the power attack. So if you see a device, so this device we are replacing it with just a system kind of thing. So a plain text and embedded computing hardware and a cipher text. So what these attackers do is that they connect that pin, I mean the power pin or whatever, to the PC USB, and the other one will be through oscilloscope. So on this device, uh, I mean they observe the power analysis as shown below. So for what happens is that uh, whenever we make a transition from either 0 to 1 or 1 to 0, there will be a power difference. Like I mean the power consumption varies. Like for when you're transition from 0 to 1, the power transition is different, and when you're from 0 to 0, there is no I mean there is no change in the power. But when you're changing the bits, like from 1 to 0 or 0 to 1, there is change in power. So the below shows a power analysis graph. So with this, uh, they come to a point that what are the bits present, like 0, if 1 you are getting a spike. So there may be a transition from here 1 to 0 or 0 to 1. So in this way they will get to know the revealed information. So as you see, the attacker will take this data and then they run a series of statistical analysis uh, to I mean to find the information. So say now we implement an RSA. There is a algorithm called RSA algorithm in hardware security. So what happens is that in order to make encryption, whatever the data is there, they for 1 they square and multiply, and for 0 they just make addition. So when you take a multiplication operation, it requires more power, and when there is a addition operation, it requires less power compared to multiplication in hardware realization. So this may, by analyzing this part of the power, so they can come to an understanding of what is happening, like where is the transition happening, and what is there from 0 to 1 or 1 to 0. So before going to the implementation part, I just want to make you all understand an S box. So on this part, there is an AES architecture, advanced encryption standard. So there is an S box. What happens is that our data, which we send input plain text, say we are sending input plain text, that has to be encrypted, and then it has to be sent to the person who we need to. So here in the middle, it has to perform the encryption. So there will be a kind of S box. So what this do is that it makes a nonlinear transformation to our data, like from the input data, it does nonlinear transformation, and then it sends the data. Like through S box, there will be a lot of XOR gates or some kind of things like squaring and multiplying and addition algorithm kind of things. So what they just replace our original data with the other kind of data from the lookup table, and then they transmit. So this non-linearity makes it difficult for software attacker in order to realize the encrypted keys, not the hardware part, but the uh, normally in the if you want to make a software attack, then it is not an easy thing, because there are 128 bits, and as we have done encryption through this S box, it would become a difficult task. Uh, so uh, this is kind of S box, and we can our part of VLSI design is that we need to realize this S box hardware. So the advanced encryption standard or whatever architecture, that will be looked up by some computer architecture engineer, or also a digital engineer who is interested. But most of the VLSI design, what we do is that depending upon the specifications, we try to design the hardware part of it, like the circuit realization or anything. So I'll show you how we do that. Now, role of this analog VLSI in SBox implementation. So most of it is digital part, digital component, but where does this analog circuits contribute to? Like they need to generate a true random number generators, like in order to provide random seeds for this encryption. Like this S box will replace the data from your lookup table. So for that lookup table, in order to get the random seeds, or you need to replace it with the random bits where you are getting from is through true random number generators. And how do you make a true random number generator? That is through analog circuit design, which I will show you in the later part. So this is for the randomness and key generation, we use true random number generators. And for mitigating the side channel attacks, what we do is generally we inject some random noise into the power supply. So so when the noise is corrupting our signals, not heavy amount of noise, but the uh, which is reliable one. So this masking of power, we can do masking of power variations. And also for as our power analysis is varying over here, if you see in the down from 0 to 1 or 1 to 0, this is how they are able to know the encrypted bits, right? So what if we just make this power consumption a constant one, like not a varying one? How can we do that? Is through dual rail analog circuits. Like if you use +5 -5 volts, like not 0 5 logic, I mean 0 or +5 volt, we use dual rail analog circuits, so that power consumption is minimum, sorry, not minimum, constant. So this in software part, they called as dummy multiplication. Like for 1, you're squaring and multiplying, but for 0, when you multiply it with 0, it will just result in 0. So without that, what we do is, without taking a 0, we take the negative power supply as 0, like -5 volt or -1 volt, and then we square and multiply. Then the power will be constant. So by that way, we can get rid of some power attacks also. But again, that will not let you through differential power analysis. That is only for SPA. And for DPA, again, they perform some statistical analysis, which is to which we should get rid of through other techniques. Like also timing stability. If you do not have some correct way of clock, so there is a clock skew or clock jitter. Now, what happens is when you're transmitting, your clock can come at some time, and your data can come at other time. So if your clock is not oriented properly, so through the timing, through the timing analysis also, the data can be leaked. So for that, we use PLLs to ensure your clock is clean, and your clock is generally there is no, there is no phase lock loop, means the phase is correctly arrested between both the signals. So there is no, uh, there is uh, what do we say? I'm not getting the correct word, but timing stability for between the two signals. If your clock is delayed by something, and if your data is delayed by other part, so if you do not receive the data, I mean, if they can analyze this part, then also it will there will be a vulnerability. So for stable clock signals and for clean clock signals, phase lock loops are used. So which are critical in SBox operations for timing. I mean for for encryption algorithms. So this true random number generator can be implemented in this way. Like we need to generate some ones and zeros randomly, and that too we need to inject some noise also, right? Which I've shown over here, so that masking may happen. So for that reason, we have put some resistors over here. So resistors have inbuilt noise with this physical phenomena like 4 kTr. So these resistors also contribute to noise. So then that signal will be given to the chain of inverters. If you take 3 inverters, then it is a ring oscillator, and that output you'll get some random ones and zeros, which is masked by this uh, noise. And at the other part, how can you implement this true random noise generator number generator is that through this part. Like here you have a comparator. I'll explain this circuit in detail. So first you have a comparator and then slicer, and then we store that information using a D flip-flop, which is driven some by output driver for amplification. And here, if you see, there is a pattern of TRNG, and this is also affected by noise for a masking purpose. Like when they analyze you, they should not be able to reveal the data. And how this circuit functions is in this way. I want to give you a different dimension in this, design, like just not showing a circuit and saying that it will function, but uh, give I will give you the insights about how this circuit works and is going to function. So this we have set it as a comparator, but why do we need this kind of transistors over here, or what is this acting like? So I'll try to explain this in more detail so that so that it will be more clear to you, and you can even get a knowledge of analog design through this. So this part, uh, is this visible? Hello.
Visible, sir.
Yeah, thank you.
Yes, sir, visible.
Yeah, okay. So this part over here is a single transistor. So when we connect two transistors in parallel, if it is same width WL and WL, it will be WL plus WL, 2 times of WL. So this is a single transistor, and above we have made a differential configuration. So this is this is what differential amplifier inside differential amplifier looks like. So so here we give some common mode signal and input differential VID by 2, and here we give this may be minus according to your polarity, VCM plus VID by 2, plus or minus. I'll show how signing convention also goes. So if you take a resistor over here, and this we connect it to VDD. Normally this is a differential amplifier. So now how do we go to the comparator stage? I mean, why do we need this part of circuitry over here? What is this doing? And why do we need these two transistors over here? So this is all clear, right? This is just a differential amplifier that that one normal makes. Normal kind of differential amplifier. Now, if you take an output over here, V naught. So if you want your output to be positive, so this is common source configuration. So if this is common source configuration, now what input you must give over here? So differential means we'll be giving a phase shifted version, right? I mean, if you give a positive signal over here, then you'll give 180 degrees out of phase shift over here. As you want, as we'll be able to, as we are giving the differential signal. So if your output is positive over here, so common source makes a 180 degrees phase shift. Then here you need to give a negative input. I mean, negative part of the signal through 180 degrees phase shift. And here you need, this is negative means this is positive. So this is the signing convention. And now let's analyze how to implement these resistors. So normally what happens is that there is a parasitic capacitance over here also. And there is also a parasitic capacitance over here. So ideally your output is like an RC circuit over here. It is like an RC, it is looking like an RC circuit. Now for an RC circuit, if you give a step input, what happens is that it will take an exponential way of rising in this way. Hope you all know this. So it will depend in how fast this rises will depend on your time constant. Now, but for your comparator, if we go through, I mean, if we use the same kind of circuit over here, whenever your input comes in this way, but you're taking this long to make your decision or give your response. So your response would come over here, somewhere over here. If you are given input over here, that means at here there may be another input. So the circuit doesn't work, right? I mean, it can't it can't give you the correct output at the correct time. Like here there may be 0, 1, it has to compare 0 and 1, it has to give the output over here, but it is giving the output over here. So due to this, we want a faster response, not this type of response. So how do you make this fast? I mean, what should we do to make this fast? So if you want to make this response in this way suddenly, what will you make? So now tau is equal to some RC, right? And this exponential, I could write it as some RC into 1 minus e power minus t by tau, where this is tau. So this is tau. Now this tau is, sorry, this is input voltage Vi, V naught. Now this tau is RC. So if I increase my capacitance, my what will happen? My response will still be very slow. It will be very lagging. So somehow I need to decrease it. So what should I do then? If you keep on decreasing the capacitance also at high frequencies, there will be a parasitics over here. So there is no way that the capacitance is in your hands after at high after certain frequencies in the design. So generally here, in order to get approximately to Vi, what we can do, so in order to get this approximately to Vi, this factor has to become 0. That means my tau has to decrease. So if I make tau negative, I mean, how can I achieve negative? So time constant, you may say that it may not be negative, but I just want to mimic this kind of thing, not physically implement it through resistor and capacitor, but mimic this kind of thing using circuits. So this to make this negative, I mean to look it as a negative part. So we make this resistor as impedance as negative. So now negative resistors are not available in the market. You need to somehow mimic this thing in order to look it like a negative. That means whenever we make it as a negative, what happens is 1 minus e power t by tau. Now 1 minus e power t by tau, what does this look like? It is a sudden exponential ramp, right? Sudden exponential, raise. So this profile may look like this. I mean, it will e power a positive thing is exponential rise, so it will keep on rising, and when you hit some your saturation level, like how much a voltage can go at maximum. It can go from 0 to VDD, and when you hit your VDD rail, it will saturate. So we are able to get to this kind of thing using using this profile. That means you need to somehow make this now a negative part, and that we can do by making this resistor as negative. So now I'll show you how to mimic this negative resistance so that it will be more clear. Just a minute. So we'll look how to make this. Sorry. How to make that resistor a negative one. Now, if you assume that you have a negative resistor minus R, and you have a test voltage over here, that is VT. So what is the current generally which is flowing over here? I is nothing but VT by R, right? Just I need what is the current flowing minus some VT by R. So this is behaving like just a, if I could replace this with some current source, voltage control current source, because this is factor is VT by R and this is a test voltage VT. Now it is same, right? These both are, I mean, these both are looking alike. If you see the resistance over here, it will be a the R is V by I, V is equal to IR, R is V by I, then VT by 1 by R. This will look like same minus R. So this, how can you implement with transistor? I mean, you need a voltage control voltage source. So our MOSFETs are voltage control voltage source, like. So MOS basically, if you take common source configuration, these are voltage control voltage source. Also, we teach MOSFETs as voltage control voltage source. So now I have a voltage control voltage source. This is, sorry. And I have a test voltage VT. Here also, this is voltage control voltage source. And this is some voltage VI. And this is GM times VI, small signal model. This is MOSFET MOS small signal model. Now, what do we need? I mean, we need VT by R. I mean, minus VT by R or VT by R. I mean, minus VT by R, sorry. This we need. I mean, this current we need. So I need to connect this input to minus VT so that here VI GM times you get minus VT. And this GM, you can make it as a 1 by R using the design steps, like whatever the resistance you need, you can make it like through GM root over 2 ID mu and CXW by L. You can make it to whatever required value of R. So that means I can by connecting my, this is MOS small signal model, by connecting in this way, this is source, this is gate, and this is drain. My gate to minus VT, I could achieve this negative resistance. I mean, kind of minus VT bar, which means the resistance is negative. So now, where should I connect? I mean, where should I connect this gate pin? This is gate, right? somehow I need to connect it to some negative voltage. So where should I do that? Now, as I said, as I've discussed over previously, that sign convention, like if you need V0 to be positive over here, then this is negative. Then this positive, then this will be minus. So that means over here I can get a negative voltage. So your gate, you are connecting it to over here, negative. And similarly, this gate, if I connect it to this side, or this side, so this will make this configuration, right? Where is that? Yeah, negative resistance configuration. So through this, if you analyze this using a small signal model, as gate, we need to connect it to the negative voltage. So what I'm doing is that through sign convention, I know that if I want to make this output V0 as negative, I somehow I need to connect it to I mean, this will be positive. And if this is positive, then this side is negative and this will be positive. So that means I'm getting a complementary signals at these two points over here and over here. So I should interchangeably connect the gate from here to here and here to this side, so that this will mimic the negative resistance. And if you even analyze this circuit using small signal model, this part, only this part, you'll be able to see that this is my in the resistance series minus 2 by gm. So this is why this makes the positive hysteresis kind of thing. So this is why you use this type of configuration for normally in comparator circuits. And for this transistors, what happens is that when two inputs are compared, normally you here, after comparing the inputs, the comparator will generate outputs like 1 and 0. I mean, in digital. So in analog, it will be a VDD and the other part. If it is connected to ground, it will be 0. Or if it's connected to the negative rail, it will be a minus VDD part. So now in the next part, so one of the input may be less than the other input. So for the first input, let's assume that input 1 is greater than input 2, and your outputs are settled to VDD and 0. And the next part, uh, the other input 2 is getting higher than input 1. Then your output should also change. I mean, if you are getting positive for whenever input is high, I mean, input is greater. So that means for the next part, when your input changes, here it has to go to 0 and here it has to go to VDD. Now that to make such sudden transitions, it has to draw a large amount of current. I mean, through this pair, it has to draw a large amount of current, which leads to high power consumption. So normally you include these switches. Once the comparison is done, what you do is you make these nodes reset to the initial values, like to VDD, so that when the next transition happens, if it has to remain at VDD, then it will normally remain at the same stage, or if this goes to 0, then it will be in the same stage. So you're resetting your output as soon as your comparison is done. So this is how the circuit works like. And slicer is normally for uh, keeping your input levels to the part which you require. I mean, if you require your output to be a certain levels, like not very high voltage levels, like say you require from 1.5 to 1.5, it is like kind of clipper itself. And then you need to store this information somewhere. Like as this comparison happens, it will generate an output. And this output you need to store somewhere, right? Uh, uh, for outputting. So for that we use a flip-flop. And flip-flop output driver is just like amplifier in order to amplify your signal and generate a random bit stream. And this is how this circuit works like. And going through the next, this is how TRNG implementation is done. And for clean and clock signals timing issues, we generally go for phase lock loops. So here I'll show you the Cadence implementation part also. How do we implement in Cadence at the circuit level? So before that, I'll just give you some basic introduction to PLL. So uh, normally when you have two clock signals, or say you have a crystal oscillator of 25 megahertz, and you need to generate a clock of say 1 gigahertz or 2 gigahertz or of your own wish. So how to do that? I mean, crystal oscillator is of 25 megahertz. It's fine. In market, you can get a 25 megahertz or 50 megahertz, or say at most not greater than 50 megahertz, a crystal oscillator. If you go on looking for a crystal oscillator which is generating some 100 megahertz or 1 gigahertz, then size will be very huge, which is not realizable. So these crystal oscillators normally they produce very clean kind of signals, like quartz crystal oscillator, something that. But from that, when you need a high clock for your CPU, like 1 gigahertz or 2 gigahertz, that you realize it to your PLL uh, by using a frequency divider in feedback path, so that your frequency gets multiplied. That is one of the application of PLL also. Normally, not only just making two clocks align correctly, I mean your system clock and the other clock. Normally what happens is that, say your clock input clock is looking in some way, and at the output side your clock is looking in the other way, or when it has gone through some path in your circuit, the clock will be delayed. But if your clock is delayed and your input clock is different, the data will be streamed as per input clock but not as per your system clock. So in order to make this both aligned, I mean to make this both stable, or say make synchronously, we use PLLs. So so this is a basic block diagram of PLL. What we have is a phase detector, a loop filter, and a VCO, and then a frequency divider. So phase detector, what normally it does is that it compares two inputs, and it generates a phase error at the output side of this phase detector. That phase error is proportional to some voltage V, and this voltage we let it through VCO. Why we use loop filter is that we, in order to get rid of the unwanted kind of frequency part from your uh, I mean from your design. I mean, so then your voltage, some DC voltage goes through here, and that VCO, what is a voltage control oscillator? So if you give a some kind of voltage, it generates frequencies. Now that frequency you're feeding it back to the phase, that signal you're feeding it back to the input of the phase detector again. So it constantly, it simultaneously, I mean it repeatedly it compares the two inputs and generates a phase difference. That phase difference is again converted, the phase difference over here is proportional to the voltage difference between these two. So phase difference between these two, and that voltage you again give it to the VCO. So this implementation, which we have done in Cadence, is a type 2 PLL, which I will be showing you. So before that, I'll show you the type 2 PLL architecture. So in type 2 PLL, normally we have phase frequency detector. This part is a phase frequency detector, which has two D flip-flops. And then we give it to the charge pump. I'll let you know why we use charge pump. Then a loop filter, and through VCO, through feedback, we feed it to the phase frequency detector again. So normally what happens is that this is a phase frequency detector. Yeah, hello. Yeah. So yeah, someone has unmuted their. I think I can continue. So these two are the, assume that these two are the inputs. So this is input A and this is input B, and these two are not aligned, right? Properly, they're not aligned. So you need to generate a what this phase frequency does is, somehow by seeing this phase difference, it need to generate a signal. So here what is the phase difference between these two? This is the amount of phase difference it has. So it will generate in this way. And this QB, normally this is the QB. So this it is generated due to some suddenly when if this input is leading this input, then QB will be generated. But over here QA is leading. So QA itself will generate. This is due to some D flip-flop irregularities, like there may be gate level delay or some kind of thing. So that's why you get sudden short spikes over here, which is of very minimal time. And these are like pulses, right? But you can't give pulses to VCO directly. So for VCO, you need to give a DC voltage so that it can generate frequency. So how to generate a DC voltage now? So that part is through charge pump. So this we call it as charge pump. There are two switches and two current sources. And normally what we do is that if we give this QA signal to this switch, this switch normally acts like switch is nothing but a MOSFET. So if you want to implement it through transistor level, it will be a MOSFET, and this will be also MOSFET. So this will be on. This current will be injected into the capacitor, and capacitor starts charging in this way. So when capacitor starts charging, you will be getting a voltage DC kind of voltage over here, V. So that is shown in this way. So V out. So as this voltage is generated, this VCO will normally acts like a voltage control oscillator. That means it will generate frequency and it will feed it back to the input. Now let's see the implementation of this PLL. So in Cadence, this is the schematic level phase lock loop. Here we have a phase frequency detector, charge pump, loop filter, VCO. Now this is how a voltage control oscillator VCO is implemented. This is a current starred VCO kind of architecture. We have a ring oscillator in this fashion, and here we have why I'm saying current starred is that normally we make it power hungry, like we need a low power implementation. So we do not allow the unnecessary amount of current in order to drive this ring oscillator. So instead we make this kind of configuration. This is a current mirror kind of configuration. So these transistors are stacked upper in the up part and also in the down part as well. So here this is the kind of ring oscillator fashion. At the output side, we have put two inverters. I mean, two inverters is nothing but to buffer the output for driving the next circuit. I mean, next block. So what happens is that if you give a voltage over here, so this here we give a voltage. This is a current mirror. So through if you give a voltage over here, when it flows, this is a common source. So a voltage GMVI, a current I is equal to GMVI will be generated. That current will be mirrored over here, and the same current we are mirroring everywhere. And we know that I is equal to C dV by dt. That means C into V by T. So C V into 1 by T becomes F. So that means if you're changing the current, you are changing the frequency also. So by giving the different voltages over here, I can generate different currents. And if I generate different current, I can generate different frequencies. Like uh, this is how a voltage control oscillator in the fashion of ring oscillator, current start VCO will work. And this is the output plots of VCO. So here I have given some 0.5 volt. So here you need to give the voltage. So 0.5 volt, and this voltage in this PLL is coming through this charge pump. So for 0.5 volt, there is some kind of waveform generated. If you measure the frequency, that will be of some frequency. And for 0.6, this is the kind of frequency we're getting. So for different voltages, we are getting the different kind of frequencies. And if you want to know the tuning sensitivity of VCO, like we normally say gain radian per hertz KVCO. So this is the plot. So from 0.5 to 0.6, it is varying in this way, and in the linear fashion from 0.7 to 0.9 it is varying in this way. So that KVCO we have measured it, and we have we came to know that it is 26.1 megahertz per volt. And normally, what is a an oscillator? So according to Barkasian criteria, your magnitude of loop gain should be, I mean, your phase difference should be either 0 or 360 degrees, close to 0, and your magnitude has to be, loop gain has to be unity or greater than 1. So in order to prove that, I mean, in order to whether to know your oscillator is working like an oscillator or not. I mean, you have implemented the circuit well and good, but how do you know that this is working like an oscillator? So this is a sanity checkup for that. Uh, this is sanity checkup for that. So at your frequency, this frequency is at 800 megahertz. I mean, this we have designed it for 800 megahertz, and at that frequency, your loop gain has to be unity. So this is the loop gain magnitude, and phase has to be close to 0 degrees. So that is what we have achieved, and from this we can confirm that it is acting like a VCO. Going to the next block, the first one, this is the phase frequency detector. So I said there are two D flip-flops and one AND gate. So in that AND gate, in order to reset your flip-flops, so how do you implement a D flip-flop is in this way. Like this is a transistor level implementation of a D flip-flop, and the charge pump which I've shown over here uh, has two current sources and two switches. So this we are implementing in the circuit level in this way. So like the current source is nothing but current source. These are two switches which are uh, we I mean switches we need to operate in the linear region, right? Your MOSFET, and if for current, if you wanted to act as a current source, you need to make it in saturation region. So these two are the switches. So this is a PMOS switch, and this is an so these two are switches, and these two are current sources. So these two are acting in saturation region, and these two are acting in linear region. And you have to get an up and down pulse, up pulse and down pulse from your PFT. From here, up pulse and down pulse, this you are giving to the charge pump. So for PMOS configuration, you need to invert it and give, right? So that is the reason we have an inverter over here. And this is a frequency divider. So frequency divider, we are implemented a divide by two circuit. How do we make a divide by two circuit is that you can take a D flip-flop and you can make it in a toggle state. Like say, for example, you can draw a D flip-flop. Uh, So you can take a D flip-flop. This is a D flip-flop. This is Q bar, and you're giving the same input. Uh, I mean, by in this fashion. This is clock, and this is the input. So this acts like a toggle state, and it will uh, do the by two. I mean, frequency divide by two, F by two. So in that way, you do that, and so sorry. So this is the circuit implementation of that generally. And now I'll take you through the simulation part. Like this is how transient plot of PLL looks like. We will zoom it and see. So this we have run it for around 3 microsecond. So say this is your clock, the normal clock which you are getting from crystal oscillator, and this output clock you need to align it to this clock. So now these two will be given to the phase frequency detector. According to uh, these two inputs, it will the frequency detector will compare, and it will generate the phase difference between these two. Say now this is leading your V clock is leading your output clock. I mean from output, this is the output. So you need to align these two as the same. So but this is leading. this is the sorry, I'm sorry. So this is the V clock and this is the reference clock you are using. So according to that, your output is generated, but it has to be aligned to this. So what happens is that here, if you see the phase difference between these two, this is the amount of phase difference. And normally, when if you come in this way, if you see over here, there is a phase difference of this much. So normally, this phase difference will accumulate as per the difference between the V clock and output. And now your down pulse will also be generated symmetrically for a short amount of time due to irregularities in the uh, D flip flops which we use. And the charge pump will generate this kind of voltage. So normally your voltage is ramping up because these two are not aligned proper. These two are not aligned properly. So if you see V clock and reference clock, your V clock has to be aligned to reference clock, and your output is trying to align to your reference. I mean, this clock properly. So over here, if I see, this is my V clock, and this is your output clock. So this clock you are getting it from elsewhere, like crystal oscillator. And to this clock, you need to align your clock properly. I mean, this output is nothing but V reference. Your output is nothing but divide by 2 of V reference, right? So these two clocks you need to align properly. And how do you do that? So this is how it is shown. In order to align these two, first, here if you compare these two phase differences, according to that, your up and down pulse will be generated, and then a charge pump voltage will be a voltage will be ramping up. So as it is ramping up constantly, this will go to your VCO. I mean, this voltage will go to VCO. So at this voltage, it will generate this kind of frequency. At this voltage, it will generate this kind of frequency. So as your voltage, as your voltage is, as your, please unmute someone who is,
Yes,
please
sir.
mute
Muted, sir.
yourself.
Muted.
Yeah, yeah,
Please carry on, sir.
yeah. Thank you. So this charge pump is keeping on, this voltage is keeping on ramping up. So for this voltage, you're generating this kind of voltage control oscillator. So as you are giving this voltage to voltage control oscillator, you are getting this kind of frequency. So as voltage is increasing, your frequency is also increasing. If you see, there is a difference of frequency to here and here. So this way you can make your clock aligned. So if you see it somewhere over here, your both of the clocks will be aligned. So just to make it clear once again, what happens is that your V clock and V reference, there are two inputs. So this is coming from somewhere else, like a crystal oscillator, and this V reference, you are giving it from output. So as our job is to make these two clocks align, to make them synchronous. We are giving it to PFT. Now what this PFT will do is that it will compare these two, and it will generate some kind of it will compare the phase between these two, and it will generate some kind of some kind of pulses like this, like up and down pulses. And that up and down pulses, as we cannot directly give to VCO, we are giving it to charge pump, and we are charging the capacitor. So as we are charging the capacitor, the voltage will increase, or the voltage will change over here. So if voltage changes, the frequency also changes. Say now you have got a down pulse of this. So if you have got a down pulse of this, then charge pump will discharge. It will discharge this capacitor through this NMOS. So through this NMOS, it will, yeah. So through this NMOS, it will discharge. So if it discharges, the voltage over here will decrease, and your frequency will also decrease. So in that way, it will do that. So this is what the waveform is also telling, right? So say this is V clock and V reference, and it will generate a phase. Your up and down pulses is according to this. It will compare a V clock and V reference, and your up and down pulses are generating. And according to, as you're giving your up pulse and down pulse to the charge pump, so charge pump, there is a capacitor over there, and it is charging. So as your voltage is keeping on increasing, your frequency is also changing. So this is just zoomed version. So V clock and V out. At some point over here, your both of the signals are aligned. I mean, they are synchronized. So this we call it as lock range, where both of these signals are aligned currently, where there is no phase difference. So this part you can say that your PLL has locked to the input. Now, when it is locked, your voltage will not increase. So that is the reason your voltage is not ramping up over here. And suddenly again, when you lose your lock, your voltage will again start to raise up. So normally due to some irregularities like in the D flip-flop, what I said, or circuit level implementation, we lose lock at some point of time. At the point of time, again, your capacitor starts charging up and it will go to VCO, and again your voltage starts ramping up. So at that time, after 10 nanoseconds, we have lost a lock over here, and after 40 nanoseconds, again we are regaining the lock. If you see these two waveforms, they are perfectly aligned again. So in this way, PLL will work. And if you see the power consumption is 6 dpm. I mean, it is 4 milliwatt. So we could make some low power PLL in this way. And in order to analyze jitter and phase noise. So jitter in time domain, phase noise is in frequency domain. Like uh, in time domain, we call it as jitter. So in frequency domain, it is nothing but a phase noise. So jitter means if you have two inputs and the clock edge of one input and one raising edge of the input and the other raising edge of the another input may not be uh, I mean, your raising edge of the input may vary, right? So at here, your raising edge may come in this way. So, but if your raising edge is again coming in this way, so this only we call it as jitter. I mean, so in this way. So this jitter in frequency domain, we call it as a phase noise. And that jitter has to be minimal for some PLL operations. But if you ask me for noise generative systems, like we need to mask our bits in security realization, then we need some amount of noise is also good. So for this kind of circuit, we have got a phase noise of minus 65 dBc per hertz. dBc per hertz means with respect to the carrier, how much is your phase noise? And this is the jitter. So normally what happens is that you, for a square wave kind of thing, if you analyze your Fourier series, you expect your frequency component to be in this way. But normally, as there is a variation in this raising edge, I mean, your raising edge may come over here, or at some other point of time, it may again come over here. So as there is a variation over this, normally this will not, in frequency domain, it may not look like this, but there will be a kind of what we say skit. So SKIRT skit. So that means you are allowing other kind of frequencies over here also. So this is the part which you want, but these are also entering into your uh, entering it into your design kind of thing. So what phase noise is that? What the metric phase noise tells is that, say this is your desired one, and as we can't generate clean clocks like atomic clock from crystal oscillator, wherever we generate it through PLL, there may be a certain amount of phase noise. I mean, a clean clock is not possible. But what we try to do is that we try to minimize this as much as possible, so uh, that we measure it through the phase noise. Say now this is the unwanted carrier, and this is the desired one. So from you measure this one. I mean, in we measure it through dBc per hertz. Why? Because say your carrier is somewhere around uh, 20 dB, and this is at somewhere around 120 or 110. Say let's say 110. How much this is undesirable one, right? Only this is desired one. So how much is the difference between these two? I mean, how far your undesired component is low compared to your desired one, that is what your phase noise is. So this is how much less than this 100. So this is minus 100 d 20 minus 120 minus 100 dBc per hertz with respect to your carrier. This is carrier. This is desired one. With respect to that, how much is your desired component, undesired component low? So the more it is, the better is the system. I mean, we need more minus 80 dBc per hertz is normally a good one, minus 70 dBc per hertz. But as we want some noise to introduce, so I have used a current start VCO. So more, we can't get a good amount of phase noise more than this minus 65 dBc per hertz. And jitter, as I said, this is 9.543 picosecond. So this is how a PLL works. And just before that, the other thing which I want to, which I forgot, I mean, didn't forget, but which I want to give some extra explanation regarding this true random number generator is that in this comparator part, uh, over here, when the inputs are changing, I mean, say this is the differential part. You are giving one input over here, other input over here. This VID is greater than 0. So if your VID is greater than 0, assume this is VY, this is VX. Your VID greater than 0 means if you assume this V1 and this V2, VID is difference of these two. So that means V1 is greater than V2. That means your Vx will be a positive over here. You will see a positive going to VDD, and your Vy will be going to 0. How that is possible is that normally in the circuit operation, what happens is in this way. So when your V1 is greater than V2, in this branch, current is uh, oh, in this branch current the current is flowing more than this branch, as V1 is higher, I1 is greater than I2. So if your I1 is greater than I2, so this node voltage is trying to pull lot of current from here. So that means this voltage will be less than this voltage. So here you'll be your voltage will be reducing, and here your voltage will be increasing. So that means Vx is reducing and Vy is going positive. And when you give a negative voltage to this one, so again it will generate as this is PMOS, this is on, this is off. So now it is generating a current I1 which is again greater than I2. So this kind of repeats in this fashion, and your Vx terminal will go to VDD, Vy terminal will go to 0. This is fine. This is the first comparison. In the next cycle, say in the next clock cycle, say your V1 is less than V2. So that means VID is less than 0. Now Vx has to go to 0 and Vy has to go to VDD. So this sudden transition, uh, takes a lot of current from the differential pair in order to make this transition, like from 1 to 0 and 0 to 1. So in order to get rid of that, we introduce two switches. As soon as your comparison happens, uh, it will normally take some time in order to generate the response. So at that time, what we normally, so say in this clock pulse, you are sampling, and in this clock pulse you are generating the I mean taking the decision. So whenever, so that means again here sampling will takes place. So at that point of time you're resetting your node voltages over here to VDD, so that it will be again to VDD, and this transition, sudden transition, if this sudden transition, even if it want to take place, it will just be at the same position VDD, and it will not that huge amount of current it has to make in order to make this transition possible. So that is the why we use here switches switches also. And I think that is clear. And if you see the challenges and future implementations, like there are power constraints in any VLSI chip. If you take, the power and area are very important. So as I said, we need to go for a low power design in our chip. So there is a power constraints, achieving security in low power environments like IoT devices, and noise and bias. So we normally, for randomness in TRNGs, we need noise to make that masking possible. But again, if you are keeping on introducing noise, you may also will not be able to decode properly at the receiver stage. I mean, if your noise goes uh, uh, out of the realizable one. And area efficiency, again, area wise, we need to shrink these transistors as much as possible. And when you're going to some lower technology nodes, you may encounter some sub-threshold current leakage, or sub-threshold effects, and even your square law doesn't work. So that will be a difficult task to go. And normally what the future directions is that uh, not completely realizing TRNGs using analog way, but both combining analog and digital techniques for more reliability. And as we have come down to 3 nanometer or 2 nanometer these days, yield is also very less. So in order to swing more and more, uh, Moore's law, according to Moore's law, or electronically, it may not be possible. So we are looking for some advanced materials like MEMS-based noise sources, in order to make our compact chip. I mean, the area-wise, a very small chip, and also in order to shrink the size. So artificial intelligence assisted VLSI design is also a booming for implementing the analog circuits in secure systems, which is yet to come. So in this way, I can say that these circuits play a key role in secure communication systems. So like from ensuring signal integrity to generating secure keys in the way that random keys that we are generating using TRNGs. So this is how a cryptographic process takes place. And uh, by both combining digital techniques and analog techniques, we can go for reliable VLSI design. And this I can show you through Karen software also, but unfortunately I couldn't access my server, so I could get this uh, get this I mean what we call get these screenshots of the design. So hope it was clear, and sorry for that inconvenience. And with this, I end my uh, lecture on this part, and hope it is it has some good information to take away. So thank you everyone for even attending this session in your personal time after your professional timings. And if there are any questions, I would like to have those questions. Yeah, hello, Vasu sir, please, over to
Yes,
you
sir.
if there are
One
any
question
questions.
from chat box.
Yeah,
You said that this PLL clock circuit requires 4 milliwatt power to
yes.
generation, but when this clock is applied as input to other circuit, how much power this circuit can supply or handle?
Uh, Sorry, can you repeat that properly?
PLL clock circuit requires 4 milliwatt power to
Yes,
generation,
yes, yes, yes.
but when this clock is applied as input to other circuit,
Okay,
how much
okay,
power this circuit can supply or handle?
okay, okay, got it. So this PLL, normally you use it for in your system. So normally this PLL is taking, this complete system of PLL is using some 4 or 5 milliwatt of power in order to function. So this PLL will not deliver the it will not deliver the power, or it will not supply any power to the next block or next circuit. Just it will give you the correct synchronized clock. That's it. So for the amount of power that you need to get, that will be generated again by using power management integrated circuit for the whole system. So PLL function is to just generate a synchronous clock. That's it.
Thank you, sir. Any questions from participants? Please unmute yourself and ask. Sir, one more question.
Okay.
How you check the randomness property in the true random number generated?
Okay, so normally what happens is that in there are two kinds of random property. One is true random number generator, and other is a pseudo random number generator. So this uses some deterministic algorithms in order to generate the randomness, like 0, 1 or something. But this uses the physical phenomena, like as I said, the noise sources. So normally there is a profile over here, right? So so in this way, so if you're increasing, say if you're increasing your resistance over here, then that resistance may be proportional to your 4 ktr also. So this is the amount of noise you're contributing. Say this is this is the noise factor your resistor is generating. Now if you're keeping on increasing the resistance, that means if you're keeping on increasing the resistance, you're also increasing the noise over here. So if you are increasing the noise over here, at the output also that randomness will be synchronized, right? If you have a good amount of noise, then there will be a lot of randomness like this. So if you are decreasing your resistance, or if your voltage source is not that noise, then I mean these MOSFETs also generate a noise like 4 kT gamma GM. So if you are according to your transistor sizing, if your noise is not up to the mark, so your randomness uh, may be less. So depending upon the design, like your resistor values or your circuit component WBL values, your randomness varies, and that you can observe in the voltage versus time profile at your output side.
Okay, thank you, sir. Any other questions from participants? Please unmute yourself and ask freely.
Hello, sir.
Hello. Yeah.
This is Anita from Amrita Engineering College,
Hello.
Bangalore, Karnataka.
Yeah.
Thank you, Sai Charan, sir. It was hello.
Yeah. Hello. Thank you, ma'am. Thank you.
It was very nice session, sir. It was fruitful to each and every person. If sir, can we contact you for any further discussion, sir?
Sure, ma'am. I'll drop you an email over here. So.
Okay, sir. Okay. Thank you very much, sir. It was very nice session, sir. Thank you, sir.
Thank you, ma'am. I'm dropping an email over here so that you can
okay, sir. Okay.
So
Okay.
hope you can see this mail.
Okay, sir. Yes. Thank you very much, sir.
Yeah, thank you, ma'am. Are there any further questions?
Okay.
Yeah,
Good
okay.
evening. Okay.
Just a minute, sir. So
Okay. Yeah.
before
Yeah,
just a minute for everyone. So as everyone is most of the faculty over here, and you are very experienced, then you are very experienced. So my experience is not very huge before. I mean, I'm just a uh, recently kind of guy, MTech graduate. But one thing I would like to pass on from my professors at IIT KGP is that we need a semiconductor workforce development in our country. Like we are going ahead through Indian semiconductor mission, and I generally request all, as there are many faculty, to keep your students posted about, I mean, let them know about this and make them to go for higher studies as much as possible to pursue their masters in IITs or some premier institutes like ISC, whoever is, whoever is willing to. So not only there are coding jobs or IT related jobs, but there are also huge requirement for in the semiconductor development in the future. So if we fall short of the semiconductor development, then our country or we may not, we may not again see such huge rise up in our in our semiconductor field. And also this semiconductor field is not only about designing your analog or digital circuits, but it is also about uh, generally researching about the materials also. So there are many faculty in IITs who research on materials for replacing our silicon or germanium. Say for quantum circuits, you need different kind of material, superconducting bits or kind of that. So this plays a huge role. So VLSI is not just confined, or semiconductor is not just confined only for VLSI. It requires a huge knowledge of device physics, material physics, and also VLSI. So if you are interested to take part in such 2D materials or material design or device design, you can even take up that. So it is not a limited one. And this was this was said by Professor Rao Tumala, who is one of the uh, semiconductor workforce coordinator for in our India, in our session in IIT Kharagpur. So hope you will pass on the same to the students, like make them encouraging towards the semiconductor work field, and let's contribute the same all with all. Thank you. Thank you very much.
Okay, thank you very much, sir.
Thank you.
Good evening, everyone. On behalf of the organizing team, it is my privilege to extend a heartfelt vote of thanks to Mr. Sai Charan for his enlightening session on VLSI design for secure communication systems. Your detailed insights into critical topics such as hardware security and SBox, the role of analog VLSI in SBox implementation and true random number generation implementation, and PLL design have provided immense value to our participants. The way you bridged theoretical concepts with their practical applications in defense and secure communication system truly showcased your expertise in that field. Your emphasis on innovative solutions in VLSI design for enhancing hardware security has certainly sparked inspiration among us all. This session has been an integral part of the 60th ATAL Faculty Development Program on VLSI Design Innovation for Defense Application, and your contribution has significantly enriched our understanding of the advancement and challenges in this domain. Once again, thank you very much, Mr. Sai Charan, for sharing your valuable time and knowledge with us. We deeply appreciate your effort and look forward to more such interaction in the future. Thank you, sir.
Thank you, everyone. Thank you, sir, and thank you, ma'ams. Thank you.
Thank you so
Thank
much,
you,
sir.
sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir. Thank you.
Ma'am, we are stopping the recording.
Yes, sir. Yes, sir. I think the feedback link is shared in the chat box.
In WhatsApp
No,
also,
ma'am. No, ma'am. In chat box is not there.
No, Vasai
No,
Garu, please share it in the chat
just
box.
now already said, ma'am.
Okay. So the
Hello,
link
ma'am.
will be active. Yes, yeah, ma'am.
Ma'am, I'm not able to access the chat box, ma'am. It is displaying something went wrong. Not able to put a message also.
Is it so, Anil sir? Then how other participants are keeping messages in the chat box? Anil,
Ma'am, it is possible, ma'am.
everybody is keeping. Yes.
Yes.
I was trying
Ma'am,
from the
Ma'am, it
7:30.
is
ma'am, if you have Teams
ma'am, it
app,
is
that
available
will
in a
be great.
WhatsApp group also.
Okay, sir. Okay, I will.
So yes, we are sharing in the WhatsApp also, ma'am.
WhatsApp
Okay, ma'am.
also, ma'am. You can
Okay.
So the
access
link
in
will be
WhatsApp.
active for the next half an hour, ma'am.
Okay, ma'am. Can you share the mail ID of resource persons in WhatsApp, ma'am? because I'm not able to access the chat box in this.
No, that we cannot keep it for all.
Okay.
I'll no, you message me so that I'll no keep a message privately.
Okay, ma'am. Okay. Thank you, ma'am.
Okay. Thank you.
Okay.
Ma'am, we are closing the session.
Yes, sir. Yes, sir. We can close the session, sir. Thanks. Thanks to all the participants.